Hi viewers, in this present class we will start pavement design. So normally we have two types of pavements, as we know. Flexible, as the name itself specifies, the surface of the pavement and the total pavement is flexible. And we have rigid and semi-rigid pavements. So what is a flexible pavement? We have different components in flexible pavement. We'll give slight introduction into it. So top layer, we call it surface layer. We have base, sub-base, and this is subgrade. And in surface layer we can have subsections also, some 1 to 2 layers. So this is typical flexible pavement cross section. And rigid pavement, we don't have sub-base course, we have only subgrade, base and surface. There is no surface. And what is semi-rigid? Semi-rigid pavements. So generally for flexible pavements, what will happen is the quality of the contents used in the layer goes on decreasing. As the stress goes on decreases, stress due to the load on the top of the surface layer will goes on decreasing. Similarly, the quality of the components used in the layers also decrease. But for rigid pavements, the stress is almost taken by the surface itself. So there is no distribution of the stress. But in semi-rigid, it is in between flexible and rigid. So generally we use, if you use in base, if you use some lean concrete or pozzolanic concrete like that, if you use these components in base for flexible pavements, then it is called semi-rigid pavement. So it is in between these two. So what are the examples of flexible pavements? You know, earthen roads, gravel roads, and all the bituminous pavements are flexible pavements. Rigid pavements, most of the pavements we see cement concrete roads. So there are so many types of pavements, but what we see is cement concrete pavements. And semi-rigid pavements, if you use other etc. in base of flexible pavements, it is semi-rigid. Now we will discuss different terms used in design of pavements. So design factors in pavements. First we need design factors to be considered in pavement design. First, design wheel load. Wheel load, then we have, in wheel load we have standard loads, equivalent single wheel load, equivalent have equivalent axial load. Equivalent single wheel load, and we have equivalent axial load also. So equivalent standard loads, first we see 80 kilonewton is the standard load for a single axle with the dual wheels on either side. So we have two wheels here and two wheels here. This is a single axle. On tandem axle, so there are two assemblies. We have two assemblies. Two single axles side by side. Then this is tandem, and similarly we have tridem, three of these. So standard load for a single axle, dual wheels on either side is 80 kilonewton. Generally we take this as standard load, means 20 kilonewton on each wheel, right? So what is single wheel load? We'll see now. Equivalent single wheel load. Suppose this is a dual wheel assembly on top of a pavement. Suppose D is the distance between, clear distance between these two wheels, and on each wheel we have load of capital P acting at the center of the wheel. And S, let S be the distance between center to center of these two wheels. So let us, in this concept, this is a semi-rational concept, and in this concept you will see, suppose 45 degrees is the stress distribution beneath the surface. This is the surface of the road. Pavement surface, and each wheel will distribute the stress at 45 degrees like this. And now it is said that at some point the two distributions of the stresses will overlap, and this distance is taken as d by 2. And if the depth, as the depth reaches 2 times the spacing between center to center of the then almost 100% of the distributions will be overlapped. It is not 100%, but we will take it as 100%. So each individual load will be combined as a single load taken as 2P. So at a distance of 2S, each individual load is acting as a single wheel of load 2P. This is called, so in between, at whatever depth we need, we can convert these two loads into equivalent single wheel load. So that, how to do that, we will see now. Let us say D as on log to log scale, we will draw this. So log of the load, and similarly log of distance from the top, log of the depth Z. So at P we have each individual action is P, and P and D by 2 as the starting point. So this is P, this is so as it reaches 2P, you can take vice versa also, no problem. So 2P we have 2S. In between we have some Z, wherever you can take Z. So we have in between point as equivalent single wheel load for that particular depth. So you can find out this as we know these two. And see, if the data is not given properly, you can adopt S as D plus 2A. What is A? A is the radius of contact area. So this is 2A, and this is also 2A. Then this S would be D plus A here and A here, D plus 2A. The data is given as like this. Center to center spacing between tires. (25 centimeter), and distance between walls of tires, (5 centimeter), and standard axle load on a single axle with dual wheels at either side. Load on dual wheels of single axle is 8 kilonewton. Now find equivalent single wheel load for pavement thickness of some 40 centimeter. They are given. So we will find equivalent single wheel load for 40 centimeter pavement thickness. So we know in a log scale for ESWL concept, equivalent single load concept, P is at D by 2, depth D by 2, and 2P is at depth 2S. On a log scale. Suppose this is P, 2P, so D by 2 and here 2S. So D by 2 is given as, so D is given as 5 centimeter, that is 2.5 is D by 2, and 2S is 25 into 2, that is 50 centimeter, and P, so for a single axle, dual wheels on either side, it is given as 8 kilometer, so we have 4 kilometer on either side, 4 kilonewton on either side, and for each wheel we have 2 kilonewton. So this is 2 kilonewton, this is 4 kilonewton. And now interpolation we know we need for 40 centimeter. So somewhere here we need this load. This is ESWL. We need to find out. So log of, we know interpolation, y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. Then we will use this formula to find out ESWL. So log ESWL is y minus log of y1 is 2 kilonewton is equal to log y2 is 4 kilonewton and log 2 divided by log 2s is 50 centimeter and d by 2 is 2.5 centimeter into log x. What is x? That is 40 centimeter minus log of x1 is 2.5. We know log A minus log B is log of A by B. Using this concept, this ESWL can be simplified as log ESWL at 40 centimeter is equal to log 2 plus log of 4 by 2 is 2 by log of 50 by 2.5 that is 20 into log of 40 by 2.5 that is 2.5 into 10 is 25, 40 by 2.5. So it comes as 16. So now if you calculate this, you will get some value, and if you need ESWL, say this value is as some x, and ESW will be 10 power x, whatever you value get here, and this is the ESWL you get in kilonewton. Now I will discuss tire pressure and contact pressure. Suppose we draw a graph between tire pressure and contact pressure here, say in kg per centimeter square. So as the tire pressure is 7, contact pressure is also 7. So up to this point, the graph should be coming like this. So this is the graph. As the tire pressure is more than 7 kg per centimeter square, contact pressure is reduced, right? And similarly, as this is less than 7, contact pressure is more than tire pressure. So that factor is called rigidity factor, which is contact pressure by tire pressure